Recursive binary search. In this lecture, we are going to see how recursive approach works for binary search algorithm. So the whole purpose of this lecture is to introduce you towards the concept of recursion. So in practical scenarios, wherever you want to implement binary search, or if you want to write the pseudocode or find the algorithm for binary search, always follow whatever you learned in the last lecture. In the last lecture of binary search, you learned the iterative approach. So follow that whenever you want to practically implement, because the space complexity of iterative approach is order of 1. But in this recursive approach, it is going to be counterproductive for you. It is going to add space complexity and make it log n. So because of the recursive stack, it's going to take extra space. The algorithm will use up additional space of order of log n. So the reason we have this lecture is that I want to introduce you towards recursion. If you are here to learn about the concept of binary search, then go to the previous lecture. There we have explained in detail what is the concept of binary search, how it works and all. So here we are going to see how the same approach when implemented through recursion works. So I want you to see the difference when the same algorithm is implemented in a recursive manner instead of iterative manner. So in the next lecture, we'll go in detail on what is recursion and how it works. So here I want to give you a heads up by giving a practical example of how an algorithm which is already in iterative version is converted to recursion. So in the last lecture, we saw iterative. So what is binary search? We'll have an array. In this array, if you want to search for some particular value, it will be from index 0 to let's say 7. You will first find the mid element. Mid element will be index 3. Then you will see whether your target value, say 50 or something, whatever you want to compare with, you want to search in this array, you'll see whether the target value is equal to the mid element. If this mid element is actually 50, you'll say, yes, I found the element, and you will conclude the search. If it is not 50, if this is some other element, 40 or something, you will see whether 50, the target value, is larger than this or smaller than this. If it is smaller than this, you will eliminate the right part of the array, because this array is already sorted. You know that if this value is smaller than 40, it won't be there in the right side. It can only be found in left side. But in this case, 50 is larger than 40, which means you can eliminate left side and you can find it. If it is available, it will be available in this left side of the array. So in every step, you will keep dividing it into half and go on. So this is how what we discussed in the last lecture. So here we are going to write a recursive approach. So before we write a recursive approach, what all things should you know? First thing you should know is, where would you end your recursion? What is recursion? In recursion, you'll call a function. The same function will call itself again. This function will again call itself with different values. Different values it will call itself by breaking this into smaller problem. So it will break the larger problem into a smaller problem. That is, initially it will be having the whole array. It will break it into a smaller problem of having half the array. Then it will call the same function on it. What will this function do? It will again find the mid element, find two parts, break it into a smaller problem, and call the same function for the next smaller part. This is what is recursion. So the same function keeps getting called again and again, but after breaking the problem into a smaller problem. So when you do this, the problem is you should know when to stop. You are breaking the larger problem into smaller problem and then calling. Again, you are breaking it into smaller problem, smaller problem. You should know when to stop this recursion. So what is the base condition? That is the first question whenever you are finding a recursive algorithm. So in this case, the base condition is that whenever your low index is larger than high index, that is, initially your array will have, let's say, 0 to 7, then 0 is your low, 7 is your high. Then if you divide it and you are considering only this part, then maybe this is 4 index. So 4 to 7, low is 4, 7 is high. So whenever low is less than high, there is something left in the array. Less than, or even if it is equal to high, that means there is one element left in the array to be considered. If low is greater than high, that means there is no more element to be considered. So this is your base condition. Whenever low is greater than high, you can stop recursion. So this is your base condition, whenever low is greater than high. Then you should know how to call a new function. While calling a new function, that is next recursive call, what is the condition you should do? You should have a mid value. You should compare the target value with this mid value, and you should call the same function with different low and high values according to the mid value, right? This is the logic. So let us write a recursive function and understand. A function, let us call it binary search. Binary search will have an array, target. In iterative approach, we only had to give array and target as arguments. But because this is recursive approach, you have to give the low and high values as well. So you'll see where it is used. Low and high. So these are the lower and higher indices of the array, whatever we discussed in the last lecture. Same thing holds. So what is the first thing you have to write? First thing in a recursive algorithm should be the base case. So if low is greater than high, this is the base case. In this case, what will you do? If low is greater than high, you will return -1. Why are you returning -1? Because if low is greater than high, that means search is unsuccessful. You completed the array, but you were not able to find the value. So you have to return -1, indicating unsuccessful search. So this is your base case. So writing base case at the beginning of a recursive call, that makes sure that you are always safe. Whenever you hit this condition, you will stop search there. So you know where to stop. That is the base condition. After base condition, you have to calculate mid value. How will you calculate? Mid is equal to, if mid is equal to low plus high divided by 2. So I'm putting 2 division marks. This indicates it is a integer division. That is, if the division's answer is 3.5, you should only be considering 3 instead of 3.5, because here you are looking into indices. Indices will always be integers. So you found the mid value. After you find the mid value, what should you do? You should compare this with target. So if your mid value means you have to find the middle indexed element in the array. So array of mid, if this is equal to the target value. If it is equal to target value, what should you do? You should return mid, saying this is the index at which target element is present. You would return mid value. In this case, search will end here. But if it is not found, what if it is not found? Else if, that is, if you are not able to find the target value in mid, in case AR of mid is lesser than target. If this is lesser than target, what should you do? In this case, in the previous approach, that is when it was iterative, what did we do? We simply gave low a new value. So in this case, you are going to call the same function again with a different value of low, right? Because if AR mid is less than target, that means you have a middle element. Target value is greater than this mid. Target value is greater than mid means you have to see the right part of the array, which means you have to change low value to the value to the right of mid. High will stay as it is. So you will call the same function, this binary search function. You are going to call same function again, but with different arguments. AR, this array target will hold the same, but instead of low, you will have mid plus 1. Okay, you will have mid plus 1, and high will remain the same in this case. So this is why it is called recursion. You are calling the same function but with a smaller data set. So you are decreasing the size of the problem, but you are calling the same function. Else, what is the remaining case? In this case, it will be larger than target. Let me just write it as else if, so that you'll understand what exactly is the condition. Array of mid is greater than target. So if array of mid is greater than target, what happens? Array of mid is the target is lesser than this. If target is lesser than array of mid, you have to see the right side of the array, which means you have to make the high value mid minus 1. So this time you will call same binary search function with array, target, low, and instead of high you will have mid minus 1. Okay, mid minus 1. So this is what you're going to do. So this is your complete recursive algorithm. This recursive algorithm will do the same job that the previous iterative algorithm did. But the problem is this will take extra space for recursive stack. So how does that happen? We'll see it with a dry run. Then it will be very clear for you. So let us see this with a dry run. It will be good. So we'll take an array. This is the array you are having. And in this array, values should be in sorted order. So I'll consider 13, 27, 33, 40, 51, 68, and let us say 90. These are the values in it. And the indices are 0, 1, 2, 3, 4, 5, and 6. These are the indices. So in this case, you have 0, 1, 2, 3, 4, 5, and 6 as the indices. And let us see how this algorithm is working on this array. So then you will exactly understand how it works. So let us say this is my recursive stack. So I'll have a recursion stack whenever I'm using recursion. So this is what is going to take up space. I want to show you what part is taking up space. Why is space complexity order of log n? The reason is this recursive stack. I'll show you how recursive stack is being filled up in this case. So let us start with this. Initially, you will call binary search and your low will be 0, high will be 6. And let us say you are searching for value 51. Okay, 51 is what you are searching for. When you're searching for 51, if you call binary search from 0 to 6, let us run through this algorithm and see how it works. So first it will check the first step. If low, this is the first step, this is the second step, this is third step, fourth step, and fifth step. These 5 steps it has to do. So this binary search 0 to 6, it will go to the first step. In first step, if low greater than high, you have to return -1. So is low greater than high? 0, is it greater than 6? No, it is not. So you don't have to return from here. You'll go to second step. Second step says mid is equal to low plus high by 2. So what is the mid value here? 0 plus 6 by 2, which is 3. So 3 is your mid value. So your third element, this is the third index, is the middle index. What is the next step? You have to go to third step in binary search, which is whether if AR of mid equal to target. This is the third step. If AR of mid equal to target, you have to return mid. See the target element. So target element is 51, AR of mid is 40. So it is not equal. So you don't have to return mid here. You go to fourth step. What is the fourth step? If AR of mid less than target, then you have to do this binary search again with these values. So AR of mid is 40. Is 40 lesser than target? Target is 51. Yes, 40 is lesser than target. That is correct. So because it is less than target, what will you do? You will call this one binary search array target mid plus 1 and high. So this time you will call binary search with mid plus 1 and high. Mid is 3, mid plus 1 is 4, and high will remain as it is 6. So this time you are calling binary search of 4, 6. What is the first step? First step is if low greater than high, return. Is low greater than high? No. Low is 4, which is less than high, which is 6. Oh, you don't have to return. Go to second step. Second step says mid equal to low plus high by 2. So what is your mid value now? Your mid value is 4 plus 6 by 2, which is 5. So you got 5 as the mid, which means your new mid is 68. And this much is eliminated. This left part is completely eliminated. Now only this part remains. Your mid value is index 5, which is having value 68. So you go to step 3. Step 3 says if AR of mid equal to target, then return mid. Is AR of mid equal to target? Target is 51 and AR of mid, array of mid is 68. It is not equal. So you go to step 4. Step 4 says if array of mid less than target, then you have to execute binary search. What is array of mid? Array of mid is 68. Target is 51. Array of mid is greater than target. So you don't have to do step 4. Go to step 5. Step 5 says if array of mid is greater than target. Yes, that is the case here. Array of mid is 68, which is greater than target. When it is greater than target, you call this binary search. Binary search with This time what you have to do? You have to call with low and mid minus 1. Low will hold as 4 and you have to use mid minus 1. So 6 minus 1 is 5. So 4, 5. So when you're calling with 4, 5, this time what happens? You will call first step low greater than high. Is 4 greater than 5? No, it is not. So you don't have to return in first step. You go to second step, which is mid. Calculate mid. Mid is 4 plus 5 by 2, which is 9 by 2, which is 4.5. So you will take integer part, which is 4. So your mid is 4 now. So only this part is remaining. Your mid is 4. 51 is the value. In third step, what will you do? In third step, you will check whether the target value 51 is equal to mid value 51. Yes, it is, because AR of mid is 51. Target value is also 51. So it matched. So in third step, you understood that you found the searched element and it is at index 4. So from here, you will return the value 4 downwards. So here again, binary search of 4, 6 got the value 4. What it will do? It will return the value 4 again to the previous function. So binary search of 0, 6 is the parent one that got the value 4. So this 4 will be finally returned, which means you found the index 4 in which the value 51 is present. So this is how binary search algorithm works. So how did we calculate space complexity? Space complexity was calculated by the same technique in which we found time complexity in the previous lecture. So in space complexity, you want to see what is the maximum size of the stack. So in each step, this stack will increment by one size, right? Each step, when binary search is called, the stack will increment by one size. And in the previous lecture, we clearly saw that maximum number of steps possible is order of log n. This we proved in the previous lecture. Maximum number of steps is order of log n. And in each step, into the stack, recursive stack, one new element will be added in case of recursive approach, which means your space complexity in recursive approach will be order of log n. And what will be time complexity? Time complexity will remain the same as iterative approach, order of log n itself. So in case of this recursive approach, your time complexity will be order of log n, space complexity will also be order of log n.